In our final tutorial, we will approximate the area under a curve using an infinite number of rectangles. So let's flip over to this part of our notes, and we're talking finally about exact area. And we are doing it for right endpoints. There is another method using left endpoints, but we'll save that for a later day. So let's look at our definition. Let f be continuous. We have to be talking about a continuous curve, and it has to be non-negative, meaning that it's above the x-axis. This continuous non-negative curve will be on the closed interval from a to b. If that's all true, then the area bounded by the curve, the x-axis, and the vertical lines x equals a and x equals b is given right here. Here is our formula. Our area will be the limit as n approaches infinity of the summation as k goes from 1 to n of f of a plus k delta x times delta x, where delta x is b minus a divided by n. B and a, of course, coming from our closed interval. Let's talk about what this means. Let's start with delta x. This is ultimately our width. We're taking our two vertical line values, the bigger one minus the smaller one, and dividing by the number of rectangles. In this case, we'll just label it as an n. This is our width of each of our rectangles. And if this is our width, then this would represent our height. Remember, the height changes depending on what our function is doing. So f of this is going to represent our different heights. This is our width, and depending on which rectangle we're talking about, k is this variable. So the first rectangle, k would be 1, the second rectangle, k would be 2. And you can see that k is going to be growing from 1 all the way to whatever n is. So each one of those rectangles, that width, plugging it into f would give me the height. We have to put this extra a plus that because we might not be starting exactly when x equals 0. So wherever we're starting for a, we have to account for that right here. So let's talk about this more. If this is the height and this is the width, and we multiply them together, well, then this represents the area of any one rectangle. And the summation would be adding up all of the areas together. And the limit as n approaches infinity is trying to find that limit as the number of rectangles increases to infinite rectangles. So that is very nice. That puts everything together very nicely. And we'll see how we can use this formula in our next example. Here we go. Example 2. Find the area bounded by the curve f of x equals x squared, simple parabola, between the vertical lines x equals 0 and x equals 1. I think the first thing we should do is just draw a quick sketch of this curve. Let's just see what we're talking about here. I'm just going to draw a quick sketch. Here's 1, 2, 3, and -1, -2, -3, and here's 1, 2, 3, 4. This is just a simple parabola, y equals x squared. So 0, 0 is the vertex, and 1, 1 is a point, and 2, 4 is a point, and 3, 9, but I'm not going to put that. -1, 1, and -2, 4. Just generating some points here. So this is my curve. Okay, and we're looking for the area under this curve between x equals 0 and x equals 1. Well, here's x equals 0 and here's x equals 1. So I'm going to draw a vertical line there. We're talking about this area. No, this is not the area of a triangle. Remember, this is a curve. It's close to being a triangle, but it's not. So that's ultimately the area that we're looking for. So let's write down our area formula. Area equals the limit as n approaches infinity of the summation as k equals 1 to n of f of a plus k delta x times delta x. This is our area formula. We're going to plug into that. What I like to do is find what delta x is and then find f of a plus k delta x and plug into this. So let's go off to the side and do that. I'm going to do delta x over here. Delta x is b minus a divided by n. In this case, b is 1 and a is 0. b is 1 and a is 0. So this is simply going to be 1 minus 0 divided by n is going to stay n. So this is 1 over n. Put a box around that. That is going to go right here. Okay. Next, I'm going to do f of a plus k delta x. Let's see what that's equal to. Actually, before we say what it's equal to, let's put in some of these pieces. A is 0, because here's A. Here's A. Plus k is k. K is just going to stay k. That's our variable. And delta x we just found is 1 over n, so that's 1 over n. So if I simplify this a little bit more, 0 plus this, k times 1 over n is just k over n. So f of k over n. Let's go remind ourselves what f of x is. F of x is x squared. So f of k over n would be k over n squared. Or rather, k squared over n squared. And that's that part. And that's going to go right here. So we have our two pieces. We have our width, that's here in red, and we have our height, that's right here in blue. Let's write that all into our area formula. We'll deal with the limit at the end. We'll deal with our summations soon. Let's color code here. Our blue part is going to be this k squared over n squared. I'll go ahead and put that in parentheses. And our red part will be 1 over n. Here's our width, here's our height, and now we have our problem. We'll deal with the limit at the end. We're going to do our summation right now. So using our techniques from last class, I see this constant of 1 over n. In fact, I see another constant of 1 over n squared. So I can just take that all out as a 1 over n cubed, right outside the summation, not past the limit. We'll deal with the limit at the end. So we've got the limit as n approaches infinity. I'm taking the 1 over n squared out and the 1 over n, so that would be 1 over n cubed is coming out as a constant. And then my summation, and I'll have k squared all by itself. So that's our first move. Next, I know what this is equal to because I remembered my summation formulas. So I've got my limit as n approaches infinity. I've got my 1 over n cubed. And this is going to turn into n times n plus 1 times 2n plus 1 all over 6. And that comes from a previous tutorial on our summation formulas. So if our goal now is to find the limit of this expression as n approaches infinity, I'd like to get this all to just be the one term and see each of the pieces of it. So let's see what I can do. I can actually cancel one of these n's out. This factor of n is going to cancel away with one. I've got 3 factors of n here, so I'm just going to cancel that out and say there's only 2 left, so n squared. All right, and then I'm going to FOIL this. So let's see what we've got now. We've got the limit as n approaches infinity. I'm going to make one big fraction here. I see the denominator is not too bad, so I'll put the 6n squared. And then the numerator, I've got 1 times, well, it's just this FOIL problem. So 2n times 1n is 2n squared. And the outer terms are 1n. My inner terms are 2n, so that makes 3n. And 1 times 1. I feel like we've FOILed these two together a few times, so we've almost memorized this trinomial. I'm almost there. We've got the limit as n approaches infinity of this fraction. And as you can see, this fraction has the same degree in the numerator as it does in the denominator. And in that case, we take the leading coefficient. So this limit is equal to 2/6, which of course reduces to 1/3. And that is our final answer for our area. The area underneath this curve right here is 1/3. Great problem. We have one more example, and we'll look at it right now. Find the area bounded by g of x equals 3x minus x squared between the vertical lines x equals 1 and x equals 2. So again, I think the smart thing to do first is let's just quick sketch this curve. 1, 2, 3. I'll put a fourth one. 1, 2, -1, -2, -3. I'll do 1, 2, 3, 4. And let's see what we've got. Now this parabola, I know it's still a parabola because I see the x squared. It's not necessarily in a form that's, easy to graph. I could put it in one of those forms, or I could just generate a t-table. I can just plug in a 0 and a 1 and a 2 and a 3, and let's see what happens. If I plug in a 0, I would get 0 minus 0. So that means that 0, 0 is one of the points on this curve. If I plug in a 1, I would have 3 times 1 is 3, minus 1 squared is 1. So 3 minus 1 would be 2. So plugging in a 1, I'd output a 2. Let's plug in a 2 next. If I plug in a 2, I'll get 6 minus 4. 6 minus 4 is 2, and 2 would be a point on my curve. Let's plug in a 3. If I plug in a 3, I have 9 minus 9. Well, 9 minus 9 is 0. Hey, I can see my symmetry right here. I know my vertex is going to be, I don't know, somewhere right in here. And remember, this is just a sketch, so I'll just say that it's about right there. So here's my curve. It's just a sketch, just a visual. And we're talking about the area underneath that curve between x equals 1 and x equals 2. So here's x equals 1, and here's x equals 2. So we're talking about this area right here. Kind of looks like the Washington Monument here. All right. So that's our visual. We're trying to find that area. Let's write our area formula again. I like to write this down every single time. It helps me to remember it. The limit as n approaches infinity of the summation from k equals 1 to n of, oops, not f this time. Watch out now. G of x. G of a plus k delta x times delta x. Okay. I'm going to come off to the side and I'm going to find this delta x, this width, and I'll also find this height, and I'll do that over here. I believe I used red for delta x last time, so here we go. Delta x is b minus a divided by n. In this case, b is 2 and a is 1. So this would be 2 minus 1 over n. So this is going to be 1 over n. So there's my delta x, and again, that's going to go right here. I'll substitute that. And I'm looking for g of a plus k delta x. So that's going to be g of this case, in this case, a is 1, k is still k, and delta x I had just found is 1 over n. So we're talking about g of 1 plus, this would multiply to become k over n. So plugging 1 plus k over n into the g function right here and right here for the inputs would give me 3 times my x, which is this whole thing, 1 plus k over n, minus x squared, so I'm going to put it again, 1 plus k over n, quantity squared. All right, so I got some work to do here. I'm going to distribute the 3. 3 times 1, 3 times k over n would be 3k over n. And I'm going to be subtracting. I need to FOIL this binomial. I'm going to put it in parentheses since I'm going to be subtracting all 3 parts. 1 squared is 1. The inner terms would give me 1 k over n, and the outer terms would be another 1 k over n, so that makes 2 k over n's, please go off to the side off to the side of this side if you need to FOIL this where you can see it. And then k over n quantity squared would be k squared over n squared. So that's foiling that binomial. But then I also need to subtract all three parts. So let's see what I've got here. I've got my 3, I've got my 3k over n, running out of room, minus 1, minus 2k over n, and minus k squared over n squared. Okay, and I do have some like terms. 3 take away 1 would give me 2, and 3k over n minus 2k over n would give me 1k over n, and negative k squared over n squared. So that's what I have left. Wow. Okay, and that's going to go right here in my formula. So let's substitute everything in now. I have my limit as n approaches infinity of my sigma, my summation from k equals 1 to n of this stuff that's in the box. I'll put it in parentheses, 2 plus k over n minus k squared over n squared times the 1 over n, the width. Okay, and there's my problem. So I'm going to be using my summation formulas. The first thing I see is this constant. That's typically one of the first things we're going to pull right on outside here. So I have my limit as n approaches infinity. I'll have my 1 over n. And then, if you don't mind, I'm going to split apart this into the 3 separate summations. So the summation of my 2 and the summation of my k over n and the summation of my k squared over n squared. So I pulled out the constant and separated into the 3 sigma notations. Next, I know what this is equal to. I need to pull the constant out of this individual sigma, and I need to pull the constant out of this individual sigma. So let's try and do much of that in this one step. So the limit as n approaches infinity, and I've got my 1 over n. This is equal to 2n using our summation formulas. The 1 over n I'm going to pull right outside here. And then what's left is the summation of k. And that formula would be n plus 1 over 2. And then my minus. I've got my 1 over n squared constant that's going to come right outside here. So there's my 1 over n squared. And then the summation of k squared would be left. And that's the n plus 1, and the 2n plus 1 all over 6. Okay, we're getting there. Lovely, we're getting there. I just need to take the limit of this big thing. But before I do that, I want to kind of get rid of my parentheses and get individual pieces. Let's see what I can do. I can cancel out this 1 factor of n. That's gone. What can I do here? There's a factor of n here, which I can cancel away, and I'll just make 1 factor left in the denominator. I believe that's good for now. Let's see what happens. The limit as n approaches infinity. I'm going to leave this 1 over n for one more step maybe. I've got my 2n, and I've got my plus sign, and let's see, this is really just n plus 1 over 2, so I'll just leave it like that, minus. I'm going to FOIL this. We FOILed that last time. We got our 2n squared plus 3n plus 1, and the denominator is n times 6. Give me 6n. Close that parenthesis. I'm getting closer. Let me just distribute this 1 over n, and then I should be there. Do in red here. The limit as n approaches infinity, I'm going to distribute this 1 over n here, and here, and here, to those 3 terms. So 1 over n times, if you want to put that over 1, the n's would cancel away, and I would just get a 2. Okay. And the 1 over n times this, well, the numerator is not going to change because multiplying by 1. and n times 2 is just 2n. And then 1 over n times this. Again, the numerator is not going to change, but the denominator would be n times 6n, which is 6n squared. Okay, I believe we're ready to take our limit. The limit as n approaches infinity of each one of these individual things. I'm going to introduce my equal sign, and I'm not going to write my limit anymore. The limit of 2 is 2. The limit of this, because the degrees are exactly the same, would be our leading coefficient. I see 1/2 minus. And because the degrees are the same here, the limit of this would be 2/6. So let's see what we have here. We've got 2 plus 1/2 minus 1/3. To get a common denominator, I guess I'll use sixths. So this is 12/6. This is 3/6. And obviously this is -2/6. So 12/6 plus 3/6 would be 15. Take away 2 would be 13/6. And that is our final problem. Thanks for making it this whole way. Go back and watch this if you need to. We'll practice this in class. I'll see you then. Thank you.